In our lesson from yesterday, we talked about this capital K, which is the equilibrium constant. And remember, it is the products over the reactants raised to the power of their coefficients, and it gives us information about where equilibrium lies in that particular reaction. So we've talked about K, and we just had regular K, but you should also note that K is the same thing as K sub C, so these two things are the same thing. And the C stands for concentration. So a lot of times we don't include that little c, so if you just see a plain K, you can understand that that is going to be in units of concentration. You can also talk about K in units of partial pressure of gases, and in that case they're going to have a subscript P. So anytime you're talking about the partial pressures, you have to have that subscript P on the K. If the K doesn't have a letter on it, then it means it's concentration. And Kp and Kc are related, but only based on this equation down here. So this is the equation that we use to convert from one of the K's to the other K. So Kc times capital R, and R is the same as the gas constant that we did in our KMT unit. So most of the time we use 0.0821. Times the temperature, which has to be in Kelvin because of R's units. And then delta N, that little exponent, is the difference between the moles of the gas products and the moles of gas reactants. And by moles, what I really mean are the coefficients in the reaction. So if the coefficients of either side of the reaction are the same, so if you have 2 on the left and 2 on the right, when you subtract 2 minus 2 you get 0, and anything to the 0 power is 1. So in that case, then Kc is going to be equal to Kp. So the only time that these two are the same is if the coefficients on either side of the arrow is the same, and otherwise you can use that equation to convert from one into the other. Up until now, we've talked about homogeneous equilibria, which means that either all of the things in the reaction are aqueous or all of them are gases, but that's not always the case. So what you need to do from now on is before you set up your K expression, so before you do products over reactants, raised to the power of the coefficients, what you need to do is scan your reaction and look for anything that's labeled as a solid or a liquid. So like in this reaction right here, this one's a solid, and you're just not going to include it. So you're going to replace it with the number 1. And you can just not plug it into the equation at all. And the reason is because the concentration of pure solids and liquids are not, they're considered to be constant, and so they're not changing their concentration, and so their concentration is not going to be included in the equilibrium expression. So here's an example down here. Notice that first reactant is, actually the only reactant is a solid. So when you do products over reactants, there are no reactants to include, so it's just products. If the reverse case was there, so if you had, for instance, if we flip that reaction, if we were writing the equilibrium expression for this reaction, the only product we have is a solid, and so when you set up your K expression, you would substitute just a 1 on the top, and then you would have either the concentration or the pressure, so you would have NH3 and HCl on the bottom. But if you flip that reaction, you don't have to put a 1 on the bottom. I do want you to note how they write these. So if you're talking about pressures, you're going to use a capital P, and then put a subscript for the chemical that you're talking about, the pressure for that particular thing. And if you're doing concentration, you're going to use brackets. So brackets means concentration, and then that capital P means pressure. And you may be wondering, why are we worrying so much about this K? The K value tells scientists a lot about the reaction. So it tells you whether or not the reaction is likely to occur. It also tells you whether a given set of concentrations represents the equilibrium conditions. And basically down here, letter B, this is going to be really helpful to you. So if K is greater than 1, just remember that K is products over reactants. So if K is greater than 1, it means the top of that fraction is bigger, which means you have mostly products. And if you have mostly products, it means the reaction goes to completion. So when you mix those two reactants, once it reaches equilibrium, most of the things are going to be products. If K is really small, like less than 1, that means the bottom of the fraction is bigger, which means you have mostly reactants, which means it didn't really react that much. And so you can even say that if it's a small enough K, you can say that it does not react. DNR means does not react. And just keep in mind that this applies only to reversible reactions at equilibrium. And the last thing for today is talking about Q. So now we're going to introduce a new constant, a new letter. Q is the same thing as K in terms of the calculation. So it's still going to be products over reactants. You're still going to raise them to the power of their coefficient. It's still going to exclude solids and liquids and only include aqueous or gases. The difference is that the Q conditions are not necessarily at equilibrium yet. So if you have a reaction, right when you start the reaction, it might not be at equilibrium. So you have a certain concentration of products and reactants that you're plugging in, but it's not at equilibrium yet. And so what you're really calculating there is Q. And so the question, when they give you information about the concentrations, if they don't tell you that it is at equilibrium, then when you calculate this fraction, you're actually calculating Q. And the reason we care about that is because sometimes they'll give you the value of K in the question, and then you can calculate Q and compare it to K. And these three things down here will really help you. So if Q is greater than K, it means the reactants are favored, so the reaction is actually shifting to the left of the reaction. So it's going faster in the left direction than in the right direction, and more reactants are being formed. If Q is less than K, the products are being favored, so it's going faster in the right direction, and if Q is equal to K, then the reaction has reached equilibrium. So again, the reason you're going to need to know this is because they'll give you concentration values, they'll probably give you the value of K, and then ask you which way is the reaction shifting. So what you would do is take those equilibrium values and plug them into this fraction, products over reactants raised to the power of their coefficient, calculate Q, and then compare it to K and use those three bullets down there to see whether the reaction is shifting to the right or to the left or whether it's reached equilibrium. And we're going to stop here for today.